everyone. This machine may look giant, but I'm actually about 12 feet tall, so don't be intimidated by it. This is a machine that we use for a great many things, including tension testing of specimens. So you'll learn in some of my classes and some of the other mechanical engineering classes about dog bones. No, not that kind of dog bone, this kind. This is one that allows us to use lots of interesting materials and test how much they are able to resist being pulled apart, and that's called tension. So tension is something that tells us a lot about materials. Is the wheel going to fall off of your car because your control arm failed under tension? Well, this is how we find out. So you want to make sure that everyone pays attention, especially if you go on to design that next Tesla, right? So one of the ways that we load our sample is we make sure that the machine is started out with a sort of a close distance. Needs to be separated for most of our dog bones types by about 3.5 to 4 inches or so. The jaws on the top and the bottom here are opened by using our crank. You want to make sure that you have them loose to start with, so that the gap between them at the top and at the jaws where they grab the sample is going to be wide enough apart that you can get a good grip. Another thing that the astute among you will probably ask is, well, how is it going to grip if you have a lot of slag you'll find sometimes on some of the samples? Well, what that's going to mean is you're probably going to have to use a hand file. No, not a power tool. You might actually have to use a hand file and do a little work to invest in your own education. Don't worry, it'll be good for you. So when we load these samples in, this particular one has already been cleaned up pretty nicely. We want to make sure to righty-tighty, lefty-loosey, so that we can get the sample in place. We want to make sure the grippers are holding on to the sample at the widest part, not at the narrowest part. And you tighten the sample ever so slightly until it starts to grip. Now you'll notice the jaws are moving upward. Well, that's great. The jaws down here move upward. So if you tighten the jaws at the top, what do you think is going to happen? Yes, you in the back. The jaws at the top are going to move down. So when those move down, what are we going to need? Well, one of the fundamental tenets of working at GCU is teamwork. So let's take a look over here at our force meter and let's see what happens as I start to crank some tension into the jaws on our sample. So what's happening to the number on the screen? It's becoming a larger and larger negative number. That's strange. Why is that? Well, what's happening is as we grab onto the sample, we have to release some of that pressure. So we have a little control panel here where we have an up arrow, and that jogs our sample up. Move this so you can see the number a little bit better. This jogs our sample up, and you can see that number goes down each time we step up. Oh, now we have just a little bit of tension on it. So that's okay. As we continue to tighten our sample, we're going to see that number change again. You don't need to tighten this like a silverback gorilla, leave those at home. You only need to be snug so that the sample is not moving around. But you'll notice again, we have too much force being applied upward, and that can bow your sample, which you don't want. So you have to raise the jaws up until you're close to zero. If you have a slight amount of tension, or less than a pound of what this is, which is compression on your sample, that's okay as a starting point. So before we actually run our test, and we'll talk in a separate video about the operation of the software, before we actually run our test, we want to make sure that this machine is actually ready to run. Now, one of those things is you want to make sure that these are locked in place so that the jaws can't come open during your test. In this case, they weren't, so it's a good thing we paid attention to our safety video and checked them before we started our test. So now that the jaws are locked in place, we want to close both doors. Why do we want to do that? Well, let's see if we can focus in on the sample when we hit play, and that'll tell us what's going to happen. When we go to test a sample, the software side is fairly boring. You hit the play button, and then it begins to add stress to the material. So you can hear it creaking maybe, as some of that slag comes off the end, and it adds stress and adds stress and adds stress, and it gets longer. You'll start to see the necking phenomenon, and then once it reaches a sufficient load, it will go past its yield stress, which is somewhere about right here or so. The stress starts to decrease as it continues. It starts to stretch out. You can see it changing length slightly, and then it begins to yield and fail, and then 3, 2, 1, and pop goes the weasel. There's the failed sample.
Oh.
This is why you want to be a mechanical engineer, because you get to break things, but safely. So unless you trust your classmates to have done 100% of their homework 100% correct, sometimes when you come up to the instrument, you're going to have a different position than the home position. So we always start when we're working with a test for tension or some other test. You always want to double check your position, double check what method you're using. In the case of tension, your instructor may have their own one written if you're in one of my classes. The easiest test file to start from is in our workspace. Under our test procedure, we're going to start with our tensile test demo. So this is me. You will learn to be terrified of this name probably, but that's okay. You'll learn to use this as a base file so that you can work a little bit more easily. So what we're going to do is we're going to set it to home using the controller. You can watch as this position decreases. So we're returning it to its home position. We also start out with a lesser load. In this case, the load last time it was operated may not have been properly zeroed, so it may have been under tension or compression. So when you go to, once it actually reaches home and it stops moving, we'll set the load in between. You always want to operate this device, especially with the doors closed. You don't ever want to be using the universal tester in such a way that you have hands inside when you're moving the arms up and down. These are very heavy, and there are a lot of pinch points where you can lose fingers. So when you're operating the software that controls the servos up and down, the up arrow and down arrow, that part's self-explanatory, or should be. You always want to make sure that you're not going to be smashing your classmates' fingers, because those are a lot harder to replace than gears and parts. So now that we're back at home, we can reset our load, and that will also reset our stress. So both of those are at 0. It's always nice to de-stress in the middle of a test, right? But we want to reset our 0 for load so that we start out knowing exactly how much pressure we're applying to a new sample that we put in. Once we load our new sample, we hit the play button, and if your method has been properly set up, then you should be able to execute the test without any problems, and you should end up with a nice graph that looks like this. So then one of the other big issues is you always want to be able to export the data. So when you do that, you want to come up here to the very top, and there's a few different windows. You want to view the raw test data. It looks like a table. Most data is recorded in a table. So it shows us our test data. We can move our control panel to the side, and once we have this selected, what we can do is we can save this if it hasn't been already saved. The way I have this particular method set up is to automatically save the data. So we can't save it and we can't export it, but an export file in this software doesn't really help you anyway. So when you go to open the Windows Explorer, what you're going to find is a hyperlinked file under the quick access, and it's under resources, So this one from today is our test data, and this you can import into Excel, but instead, when you go to analyze the data, which is really the most important step out of all of this, you're not actually going to be using what you normally would, which is the data import tool from a text file over here. You don't want to use that option because it will cause a lot of extra headaches. So what you actually want to do is you want to open the file from Excel. You're going to browse to that location. And so here again, under Quick Access, I'm going to find our resources here, and I'm going to change it from all Excel files to all files, and then I'm going to pick whatever I saved my file name to. In this case, this is our data file. It's going to tell you that the universe will explode. That's fine, nobody cares. And then you'll have your data. So all of your data will show up, but it won't show up here at the top. It's actually going to show up under these labels here, all the way to the right. So these are columns about AG or so on. The ones that you're very interested in are the position and the hour and minute or second. So time and position are the most important. There's also one about load in here. So farther off to the right, the AY column, the load. And then you'll scroll for about 32 years down to somewhere in the 200s, and there's where your actual data will be. So the easiest way to use this is going to be to copy over the data, paste it into another new sheet, and then you'll have data that you can actually work with, and then you can probably pass my class. $6061 aluminum. 7075 aluminum. Still got A36 round 2.